It'd be much nicer if I could show you the demo for this, but I don't have the equipment with me. Lenz's law is much better explained using demos, but we'll do our best without the demos. So you have to try and imagine, let's say we had a copper tube or some other tube made of a ferromagnetic material and a plastic tube. They're going to be the same length. What we'd get you to do is we'd get you to drop a little magnet through each of them. Now, if you drop the magnet through the plastic tube, nothing really interesting would happen. The magnet would fall at 9.81 meters per second squared towards the ground. Physics as usual, what you've learned in Physics 20. But if we did pass this magnet through this tube made of a ferromagnetic material, again like copper, the results will surprise you a little bit. You're not going to find that the acceleration is going to be about 9.81 meters per second squared. It's actually going to be smaller. What you're going to notice is something is slowing down the magnet inside of that copper pipe. And what we want to do is we want to find out what that is. And this has to deal with Lenz's law. What's going to happen is that as that magnet is falling through this ferromagnetic material, which I'm just going to refer to as a copper pipe just for simplicity. So if you have this magnet falling through a copper pipe, what it's going to do is it's going to induce a current in that copper pipe, and that induced current is going to produce a magnetic field that is going to oppose the motion of that magnet. So what we could say is that the direction of this magnetically induced current, it's always such to oppose the cause of that current. And this is what we call Lenz's law. So we're always trying to think opposition here. Another way that we phrase this, and it gets to the point, nature hates change. This is very much true in this scenario. Now, a question you may want to ask, and it's an excellent question, is why does the current that's induced, why does it have to oppose the motion? It's a great question. We want to think about that for a second. So we're going to pretend we live in this nice fantasy world where Lenz's law doesn't actually apply. We're going to say, you know what, that induced current's going to help speed up this magnet. So here's what's going to happen. This magnet is going to fall through the copper tube. Now this induced current is going to speed up this magnet. Now what's going to happen is when this speeds up, this is going to generate a larger magnetic force because it has a greater acceleration. This means its speed is going to increase. This will increase the size of the induced current, which will increase the force, which increases the acceleration, increases the speed, kind of so on and so forth. It's that cyclical relationship. So with that continuing increasing of speed, you're increasing the kinetic energy. What's happening is you're getting this kinetic energy for doing absolutely nothing. And if you think that sounds crazy, it absolutely is. This is a huge violation of conservation of energy. As you know, we can't get energy for doing nothing. It has to be accounted for. It has to come from somewhere. So that's one way to look at it. Another way I want to just talk about Lenz's law, why current has to oppose the motion. I want to look at this through kind of the context of, we'll call it like a bit of a proof by counterexample. It's not very rigorous, but hopefully it helps kind of just highlight the idea of what's going on. So again, we're going to imagine this fictitious world where Lenz's law does not apply. And we're going to pass this wire through a magnetic field. We're going to pass it through, and we're going to pass it through with 2 units of mechanical energy. Now in this case, with the wire moving through the magnetic field and generating this induced current, we're going to say that that induced current that happens to be generated, it's going to be 1 unit of energy. What that means is that we now have 3 units of energy. But we started out, so I'm just going to kind of box this. So the total energy that we started with is 2 units of energy. Now, if we get this induced current that adds 1 unit of energy, we now have 3 units of energy. That 1 unit of energy just magically came out of nowhere. That's not going to work. That doesn't conserve energy. So this is entirely fictitious. What would realistically happen? Let's say we push this wire through the magnetic field. We're going to start with 2 units of mechanical energy or 2 units of total energy. What's likely going to happen is that current is going to induce some energy, or some energy is going to be induced to that current. We're going to say it induces 1 unit of energy, which means that the total mechanical energy available to push that bar, in order to conserve energy, it's only going to have 1 unit of energy left, or 1 unit of mechanical energy. So what's happening is if the mechanical energy of that bar being pushed through the external magnetic field, if it's being reduced, its speed is also going to be reduced. So if EM is reduced, V is reduced. And this is kind of what we talk about with Lenz's law. If we started out with 2 units of mechanical energy, if that's what I'm going to start to push the bar with, everywhere in that system I still need to have 2 units of mechanical energy. So if I do generate 1 unit of energy through that current flowing through the wire, that has to come at the expense of something else. In this case, it's coming at the expense of that mechanical energy going into pushing the wire. So it's going to lose that unit of energy, and because it loses that unit of energy, it's going to slow down. So this is why we need, for Lenz's law, this is why we need that induced current to oppose the motion.